Moving on to the stomach, this is a storage area for food after we swallow it, after we start to masticate the food, after we create the semi-solid substance. The stomach can hold about 1,000 milliliters, and it empties at about 50 milliliters. So the emptying volume, or the empty volume, that's about how much it goes down to, would be about 50 mLs, and it can distend or stretch to accommodate a much larger volume. The functions of the stomach are to secrete gastric juices, which includes hydrochloric acid, and this helps with the breakdown of food. We have the breakdown of proteins. We have certain hormones being released in the stomach that help with the digestive process. Food is released slowly into the intestine. So again, at the end of the stomach, there's a sphincter there. And that sphincter is regulating how food is released from the stomach to the intestine. This happens very slowly and very deliberately. All of the food doesn't just flush through the intestines, right? It happens in a regulated, slow release way. Different parts of the stomach, we've looked at this already: fundus, body, antrum, right? We also have the greater and lesser curvature, and the pylori. So we talked about these parts of the stomach. In terms of the movements of the stomach is continually contracting to mix that substance we talked about. So it's no longer called food at this point. It's mixed with acid, lots of mucus. It's well masticated or crushed. And at this point, it's called chyme. And it needs to be turned or mixed or mulched in the stomach. Again, mixing it with that acid to help with the digestion. And then we have gastric emptying. So gastric emptying is where the pyloric sphincter opens and releases those contents out into the small intestine. Some structures of the stomach are the stomach folds, which help to increase the surface area of the stomach. Right? If you look at the internal surface of the stomach, you'll see it's very highly folded, and those folds help to increase the surface area to allow distensibility, right, to accommodate large volumes, as well as to allow that digestive process to begin. Those folds are called rugae, and the rugae can basically flatten out. So when you eat a large meal, those folds flatten out and allow the stomach to become twice, 3 times its size. That's why you continually, habitually overeat, your stomach can grow. It'll grow in size, it'll become very big, and you'll need more to fill it, right? Whereas if you eat moderate amounts of food, the opposite happens, right? Your stomach will constrict upon itself. It'll have a lower filling volume, and it will take less food, less fluid to make you feel full. All right, and that is because of the fold or the rugae. Let's look at the gastric pits. So the gastric pits are a histological structure in the stomach. They're basically within the stomach lining, and they lead to a deeper part of the pit, which is called the gastric gland. So the gastric glands produce quite a bit of structures. So let's look at that pit here. All right, so we move all the way down to the stomach, again, highly folded, which are called, these structures called the rugae. And if we look at the lining of the stomach, we'll see that it's not just flat, but it's thrown into these folds or these pits. So you can see the lining here goes all the way down this little pit. And at the bottom of the pit, we have what's called the gastric glands. So these glands have different types of cells that are secreting different substances with a different purpose. So the products released are pepsinogen. Now pepsinogen is made by chief cells, and as this suffix, that GEN, we talked about the suffix already, that GEN means that it's not in its active form. It needs to be activated. So it's a precursor for pepsin, and this helps with protein digestion. The hydrogen ions that are secreted by parietal cells, they make the hydrochloric acid in the stomach, which helps with digesting food. These maintain an acidic environment in the stomach. And then we have a substance called intrinsic factor. Intrinsic factor is important for the absorption of vitamin B12. There's no other way for us to get this vitamin into our cells, into our blood, than via vitamin B12, than via intrinsic factor. Okay? And this happens via the parietal cells. So the parietal cells secrete this intrinsic factor, which allows us to absorb vitamin B12. Gastrin is secreted by the G cells, and gastrin is actually a precursor for hydrochloric acid. So gastrin is the hormone that tells the parietal cells to secrete their secretions. And then mucus is secreted from the neck cells or the mucous neck cells. And this mucus is to help lubricate the gastric contents. All right, so different cells found within these glands. All right, and not to confuse you, but the gland is basically the bottom portion of the pit. So this is the pit. These are the glands, right? This is the surface of the stomach. And then at the bottom of the pit, we have those glands. And those glands are nothing more than a bunch of cells that are secreting different substances. Okay? Let's talk about the acidity in the stomach. The pH of the stomach is about 2, so very, very, very acidic. And this is needed to activate pepsinogen to its active form, pepsin. So in the absence of acid, pepsinogen is doing nothing. It's not going to break down proteins. It's in its inactive form, and it will not be activated to pepsin. Right? At this pH, we also have proteins being denatured. Right? So think about the proteins that you're eating in your diet, either flesh or other sources of protein. Those need to be broken down. That starts by denaturing them with acid. Bacteria in the food that we eat can be killed by the acid in the stomach. And then what we also want to remember here is that acid is dangerous. Like this hydrochloric acid, if you've ever vomited onto something and left it there, that acid can erode even paint. Okay, that's very strong acid. And so we want to protect the underlying structures from this very deadly acid. You don't want the other proteins in your body to be denatured by this hydrochloric acid.
So did you say that in this form, the pepsinogen is not going to form into pepsin?
Correct. Okay. It needs to be in an acidic environment. Okay. And then we have the gastric mucosal barrier. So to protect the underlying tissues, to protect the mucus layer of the stomach from this acid, there's that gastric mucosal barrier, which basically has mucus there. That mucus is a coat that protects those tissues. And the structure that secretes the mucus are the goblet cells, right? We talked about the exocrine cells or the goblet cells. All right, now so food leaves the stomach, it moves down into the first part of the small intestine, which is the duodenum. And let's talk about the small intestine. So it's another hollow tube, right? Another hollow continuous tube. It's about 8 to 10 feet long between the stomach and the larger part of the intestines. So from the stomach to the cecum, we have the 3 parts of the small intestine. So the duodenum, the jejunum, the ileum. This is the prime side of digestion and absorption. So if I asked you, what's the main part of the GI responsible for digestion and absorption? It's going to be the small intestines, right? All of the structures, all of the features of the small intestine lend themselves to absorption and digestion. That form follows function, right? So the secretions enter the duodenum, and from the duodenum, we have the opening of the common bile duct as well as the pancreatic duct. So these 2 ducts bring bile into the duodenum, and where's bile coming from? Where's bile coming from? The liver, right? So bile enters the duodenum here, as well as pancreatic juices. The pancreatic juices from the pancreas with digestive enzymes as well as bicarbonate. So bicarbonate is helping to neutralize the acidity of the chyme. So when we get to the small intestines, we no longer need an acidic environment. And so we need to neutralize that acid by secreting bicarb. And that bicarb is found in the pancreatic juices. So digestive enzymes and pancreatic juices. The second substance that is entering the duodenum is bile. Bile comes from the liver, it's stored in the gallbladder if it's created in excess, and it has bile salts that specifically aid in the digestion of fats, right? So the emulsification of fats happen via bile. All right, so absorption in the small intestine happens within the first part of the intestine length, so the duodenum and the jejunum. That's the main area we have most of those nutrients moving across the epithelial layer into the bloodstream. And so the GI system, the small intestine specifically, is arranged in a way to help increase the surface area. We talk about this. We looked at this structure. We looked at this type of anatomy. What part of the kidney tubules have this anatomy? What part of the kidney tubules have this similar anatomy? Where we have increasing surface area or absorption, or in the case of the kidneys, reabsorption. What part of the kidney tubules? Where do we have the brush border in the kidney tubules? That's the distal. Where's the brush border? We're talking about one part of the tubule that has the brush border. The PCT, the proximal convoluted tubule. So the proximal convoluted tubule looks very similar to the small intestine. We have those folds that are increasing the surface area. We have lots of microvilli, which are creating that brush border to help aid in absorption. Right? In the case of the kidneys, it's going to be reabsorption, but it's the same type of process. All right? And so the small intestinal wall, we have villi, and villi are the folds of the intestines. Right? The folds of the intestines. Within these villi, we see blood vessels. This is where the nutrients that is absorbed from the food enters the bloodstream, the blood vessels of the villi. We also see lacteals, and lacteals are also important in the absorption of fats and other substances across the GI. So let's point those out here. So we have the villi. So the villi are these finger-like projections here. Now on the surface of the villi, you'll see these even smaller projections. These are the microvilli. All right, so this kind of confuses students sometimes. There's villi, which are the folds of the wall. And then on the folds of the wall, on the villi, we have these small, tiny hair-like projections, which are the microvilli. Again, all of this is helping to increase the surface area. Increase the surface area of the small intestines. If you took the small intestine and you stretched it out completely flat, it would be something as big as a football field, right? It would be lots of surface area. But all this folding helps to bring all that surface area into this nice small space. And again, those microvilli are forming the brush border. Other structures we see here in the small intestines are the crypts of leg raccoon. And the crypts of leg raccoon are these pits that are secreted bicarbonate fluid. So this bicarbonate, again, is helping to negate or neutralize that acidic environment, that acidic chyme from the stomach. Now the crypts of leg raccoon are similar to the gastric pit, so they're that fold in the wall of the small intestine, and within that fold, we have that bicarbonate fluid. And this is where we have a lot of the absorption taking place across the small intestine. Let's talk about the role of the liver in absorption. So the liver helps to absorb nutrients that travel into the blood. Okay, we talked about a portal system in the liver. All of the blood that absorbs all of the nutrients that we eat needs to be detoxified through the liver. So from the small intestines, from the colon, from the stomach, all of that blood will then drain to the liver via the portal vein. So the hepatic portal vein is bringing that deoxygenated blood into the liver to help detoxify those substances. And then the hepatic vein is then draining that blood back to the heart, right? This makes this a portal system. Blood is going to go through a capillary bed or a vein twice before going back to the heart. And again, that helps with the detoxification of the substances from the foods we eat, which occurs in the liver. It's important to understand that blood, fresh oxygenated blood that supplies the liver, comes in from the hepatic arteries, right? So this portal vein is not bringing in oxygenated blood. Rather, oxygenated blood comes in from the hepatic arteries, which are coming from the aorta. So essentially, there are two groups or two sets of vessels that are entering, bringing blood to the liver, the portal vein and the hepatic arteries. The portal vein is bringing the oxygenated blood that has nutrients, that has the blood from nutrients being absorbed in the GI, whereas the hepatic arteries are bringing in fresh oxygenated blood. Moving on down to the large intestines, this includes the cecum, the colon, and the rectum. There's a sphincter between the ileum and the cecum. This is called the ileocecal sphincter. And again, this is regulating the emptying of the small intestine. So I keep saying this, food does not just flow through the GI tract, right? It has to be regulated at different points. We talked about the upper esophageal sphincter, we talked about the lower esophageal sphincter, we talked about the pyloric sphincter, and here, the ileocecal sphincter is regulating the movement of that substance in the GI tract from the ileum, which is the ending of the small intestine, into the cecum, which is the first part of the colon. Okay, there are structures found along the colon, which we talked about in the lab, the tinea coli, which are the bands of smooth muscle that run longitudinally along the colon. All right, let's point this up here. So we have the tinea coli, so this tense band of smooth muscle running along here. And what this does is it kind of gathers the colon. And so the tinea coli helps to gather the colon in a way that if you put an elastic in something, it would gather it. And those gatherings are called a haustra. So these pockets, these out pouches are called a haustra. All right, so think about putting a string into something and then squeezing that string or squeezing that elastic so that it sort of gathers on itself. That's what's happening in the colon. The tinea coli running down the length of the colon creates these out pockets or these haustra. Okay. Main functions of the colon are going to be for concentration of waste into feces and reabsorption of water. Right? Those are the two main jobs of the colon. The solidification, the condensation, the concentration of the waste products that we know we don't need, or there's no further absorption that can take place across these products. And so that's removed as waste. Now, we don't want to lose water the same way we don't want to lose excess water in the urine, right? In the tubules, we don't want to lose water in the GI tract. And so most of the water is reabsorbed into the colon so that it can be reabsorbed into the body, and then that solid or semi-solid substance can be created in the form of defecation. The four parts of the colon, we should already know at this point: the ascending, transverse, descending, and sigmoid colon. The sigmoid colon leads into the rectum, which opens out into the anus. Okay, this should be familiar for you. The rectum and the anus help to empty the rectum, so empty those excreted particles out into the external surface or the external orifice. So we have at this point internal anal sphincter, which is smooth muscle, again, not under our control. And then we have an external anal sphincter, which is skeletal muscle, which we do have control over. Right, so you can decide to go to the bathroom. You have voluntary control over the external anal sphincter, very similar to what we saw with the urethral sphincter. There was an internal urethral sphincter at the level of the bladder that we did not have control over. There was an external urethral sphincter at the level of the external urethral orifice that we did have control over. Right? And a similar thing is happening here with the external and internal anal sphincters. Right? Now, both of these sphincters are necessary to defecate. So if you have opening or relaxing of the external sphincter and the internal sphincter is not relaxed, there will not be defecation. Right? So there needs to be that coordination between both of these sphincters opening in order to eliminate those waste products as feces. Let's talk quickly about the accessory glands. So we have the salivary glands. We talked about those are in the oral cavity. Those secrete saliva. We mentioned the two functions of saliva to be beginning the breakdown process and lubrication. The second accessory gland would be the pancreas. We mentioned the function of the pancreatic juices. One, again, the digestion, right? Those pancreatic enzymes breaking down food. The second function of the pancreatic juices was the neutralizing, right? That bicarbonate that helps to neutralize the acidity of the chyme that's coming from the stomach. The other accessory glands would be the liver, which secrete bile. And the liver acini helps to secrete that bile, which again moves into the duodenum and helps specifically with the breakdown or emulsification of fats. All right, when you look at the substances that are found in saliva, lots of bicarbonate ions, lots of mucus, salivary amylase, which helps with the starch breakdown in the mouth, and then lysozymes. Lysozymes help with killing bacteria, right? The antibacterial substances that help to kill bacteria, fight off any pathogens or germs that may be in the food we eat, and this happens in the mouth. This is why saliva can be very important in an antibacterial way. This is why a lot of animals lick their wounds, because that lysozyme in the saliva has antibacterial, antimicrobial properties that can help in that way. The pancreas, again, has both endocrine and exocrine function. The exocrine function is going to be that bicarbonate, right? The enzymes that help break down food, lots of different enzymes, right? Relative to its weight, there is no other organ that secretes as many enzymes as the pancreas does. There's lipases, amylases, proteases, nucleases, breaking down all of those major biomolecules that we've talked about. So fats, proteins, carbs, etc., etc. Okay. And lastly, the liver. So secreting bile, the liver helps to look at function in several different ways. It helps in the storage of glucose to glycogen, the conversion of amino acids into fatty acids, right? It helps with the breakdown of triglycerides, as well as the synthesis of triglycerides and cholesterol, and lipoprotein synthesis. So lots of accessory functions are conducted in the liver. The one that's really important here is the secretion of bile, right? Remember, bile is secreted by the liver cells, and then it's stored in the gallbladder. The liver also functions in removing old, dying red blood cells from the body, recycling them, making new hemoglobin, making new bilirubin, and eliminating that throughout the body. So bilirubin is basically the breakdown products of hemoglobin. When we take a red blood cell that's old or dying or dead, and we break it down, we take that bilirubin, we exclude it from the body, and we take those substances and we make new red blood cells. Elimination of waste and toxins also happens in the liver, right? Detoxification of the blood. We have synthesis of lots of different proteins and coagulating factors that help in other functions. And we have the secretion and modification of certain hormones, glycogen, etc., glucagon, okay? All right, so we talked about all of these substances before. The liver stores secreting bile, and it's being stored in the gallbladder. We didn't talk about these two structures. So the ampulla of Vater is the area where the pancreatic duct merges with the common bile duct, and that's where it forms this ampulla called the ampulla of Vater. Okay, and then the sphincter of Oddi is what regulates the flow of pancreatic juices and bile into the duodenum. So basically, we're not just flowing these juices, these pancreatic juices and bile into the duodenum. That is being regulated at this sphincter. This is called the sphincter of Oddi.